everyone! Today we're going to talk about how to find the area of the largest rectangle that will fit inside a semicircle. To complete this problem, we'll draw a picture of the problem and write what we know, identify optimization and constraint equations, and then use the derivative of the optimization equation to find the area. Let's take a look. In this particular problem, we've been asked to find the area of the largest rectangle that can be inscribed in a semicircle that has radius r. So as with any optimization problem, you guys know the first thing that we need to do is draw a picture of what we've been asked to find and write down all of the information that we can. With some types of optimization problems like this one, remember that it can be helpful to draw the picture on an xy coordinate plane. So I've drawn the x and y axis here, and then drawn my semicircle and made it symmetrical about the y-axis. So I have my semicircle, and we know that the semicircle has a radius of r. So that means that at any point wherever it meets the x-axis here, we have a radius of r. Over here on the left, we know that we're out a distance of negative r from the origin, so I can go ahead and write negative r. We'd also be a distance of r up here on the y-axis because obviously the radius is the same everywhere. So we've drawn that information in, and then we've shown a rectangle that's inscribed inside of the semicircle. Now here's where we start assigning arbitrary values. So let's pretend that from the origin we go out a distance of x to get to the edge of the rectangle here. So we say we're at a distance of x, and let's say that the height of the rectangle here is y. If that's the case, then that means that this point here, right, where the rectangle meets the semicircle, is at the coordinate xy because we're out a distance of x and we're up a distance of y. That means also that where the rectangle meets the semicircle over here on the left, our coordinate will be negative xy. So again, we're just getting a visual of what this rectangle looks like. So now we can start getting an idea of the dimensions of the rectangle because we know the height of the rectangle is y, right? And again, we don't know what y is yet, but we know that the height is y. And we know that the length of the rectangle is 2x, right? Because this length here is x, and this length here is x. So if we want the full length of the rectangle, we know that that's 2x. So that means that we can write an area equation for our rectangle of 2x, the length, times y, the height. So area is length times height, or 2xy. We also know that the equation of a circle is x squared plus y squared equals r, or the radius squared. This should look familiar. Remember that when we're talking about the unit circle, the radius is 1. We have a radius of 1 from the origin. So 1 squared still gives us 1, and you should be familiar with the equation x squared plus y squared equals 1. That's the equation of the unit circle. In this case, we don't know what the radius is, so we just have to call it r, which means the equation of the circle is x squared plus y squared equals r squared. So now that we've got everything written down, we need to identify a constraint equation and an optimization equation. Whenever you have optimization problems like this, you'll always need a constraint equation and you'll always need an optimization equation. The optimization equation should be the obvious one because it's what you're trying to optimize. So in our problem, in our question, we've been asked to find the area of the largest rectangle. What they're asking us for is to maximize the area of the rectangle. Since we're maximizing area, the equation for area will be our optimization equation. So to give you another example, if you're asked to, minimize surface area of something, surface area, the equation for surface area will be your optimization equation. So in this case, a equals 2xy will be our optimization equation. Our constraint equation is defined by whatever we're constrained by or whatever we're given in the problem, whatever limits us. We know, the only thing we've been told is that the radius of the semicircle must be r. So whichever equation involves r is going to be our constraint equation. We are constrained within the limits of this equation here, x squared plus y squared equals r squared. So this will be our constraint equation. And what we need to do after we've identified the optimization and constraint equations is to make sure that we have our optimization equation in one variable. In this case, unfortunately, we have it in two variables, x and y. We need to solve our constraint equation for one of those variables so that we can plug into our optimization equation and get our optimization equation in terms of only one variable. So let's go ahead and solve our constraint equation either for x or y. In this case, we'll solve it for y. It doesn't matter, it'll work either way, but we'll solve it for y. Keep in mind that in this problem, r is not a variable, it's a constant, because the radius is constant everywhere, right? And this problem could have just as easily asked us to find the area of the largest rectangle that could be inscribed in a semicircle of radius 4 or 18, right? Whatever the value of r is, it's always going to stay the same. So we can treat it as a constant. X and y are our only variables. So let's go ahead and solve this constraint equation for y. We'll subtract x squared from both sides and we'll get y squared equals r squared minus x squared. If we take the square root of both sides to get y on its own, we'll get y equals the square root of r squared minus x squared. Now that we've solved for y, we can go ahead and plug this value, the right-hand side, into our area equation for y. So we'll get area equals 2x times y, which is the square root of r squared minus x squared. Now that we've plugged in, we want to make sure our area equation, or our optimization equation, is as simple as possible. And once it's as simplified as it can be, we want to take the derivative of our optimization equation. We can't really simplify this any further, so we want to go ahead and take the derivative, which we'll call a prime. Once we take the derivative, we're going to set it equal to 0 and solve for x. So a prime, notice that we'll need to use the product rule. We have two functions here, 2x being one of them, the other one being the square root of r squared minus x squared. So we're going to treat those as two separate functions and use the product rule to take the derivative. Remember that the product rule tells us to take the derivative of the first function, so the derivative of 2x we know is 2, and then multiply by the second function without changing anything. So r squared minus x squared, square root of r squared minus x squared. Then we're going to add to that the opposite case. So instead, before we took the derivative of 2x, now we're going to go ahead and leave that alone. And this time we're going to take the derivative of the square root of r squared minus x squared. So we can treat this r squared minus x squared, instead of the square root, this is the same thing as r squared minus x squared to the 1/2 power, as is any square root. So when we take the derivative of this, we'll use chain rule. Remember that chain rule tells us to take the derivative of the outside function first, leaving the inside function completely untouched, and then multiply by the derivative of the inside function. So this here, r squared minus x squared, is our inside function. The outside function is the whole thing, including the 1/2. If we ignore our inside function and pretend that it's something simple, and we take the derivative of the outside function, we're going to bring this 1/2 out in front here, multiply by 1/2. So we'll get 1/2 times, now we want to leave the inside function completely alone, so r squared minus x squared, and then subtract 1 from the exponent as we do with any derivative. So we'll get negative 1/2. And then we want to multiply according to chain rule. Now we need to multiply by the derivative of the inside function. So we're multiplying by the derivative of r squared minus x squared. Well, remember that r squared is a constant. The derivative of any constant is 0. So the derivative of that will be 0, and the derivative of negative x squared will just be negative 2x. So we multiply by negative 2x. Now we need to simplify this and then set it equal to 0 and solve for x. So here we'll get 2 times the square root of r squared minus x squared. And then over here on the right, we'll get this 2 and this 2 to cancel. We'll just have this negative 2x, which will move out in front and combine with this x here to get negative 2x squared. And then all we're left with is the quantity r squared minus x squared to the negative 1/2. If we move that whole term to the denominator, this exponent here will turn from negative 1/2 into positive 1/2, which is the same thing as the square root. So we'll get r squared minus x squared, or the square root of r squared minus x squared, here in the denominator. To continue simplifying, we'll go ahead and find a common denominator. In order to find a common denominator, we'll multiply this first term times the square root of r squared minus x squared divided by the square root of r squared minus x squared. So we'll have 2 times the square root of r squared minus x squared, this first term. We'll multiply it by the square root of r squared minus x squared divided by the square root of r squared minus x squared. This is the same as multiplying by 1 because this fraction simplifies to 1, minus 2x squared over the square root of r squared minus x squared. Now we see that we have a common denominator. The denominator of the first term is the same as the denominator of the second term, so we can combine the fractions. What we'll get is a prime equals, we'll have 2 times these two terms here will combine and the square roots will go away, so we'll be left with r squared minus x squared minus the 2x squared here, so minus 2x squared, all divided by our common denominator, the square root of r squared minus x squared. When I simplify the numerator, I'll get 2r squared minus 2x squared minus 2x squared, all divided by the denominator, which we'll save some time and denote as d. And now we want to combine the 2x squareds here. So we'll get 2r squared minus 4x squared, all divided by the denominator. And then let's go ahead and factor out a 2 and bring our denominator back. So 2 times r squared minus 2x squared, all over the denominator of the square root of r squared minus x squared. Now what we want to do, since we've simplified this as much as possible, is set the derivative equal to 0. So we set the derivative equal to 0 and we want to solve for x. The only time when our fraction over here on the right hand side is going to equal 0 is when the numerator equals 0. When the denominator equals 0, of course, the function is undefined, but we want the function to equal 0, which means we have to get the numerator to equal 0. So if we just look at the numerator for now, we can divide both sides by 2 and we'll get 0 equals just r squared minus 2x squared. We need to solve this for x in terms of r. So we'll go ahead and add 2x squared to both sides. We'll divide by 2 to get r squared over 2, and then we'll take the square root of both sides to solve for x. So when we take the square root of both sides, we can deal with the numerator and the denominator separately. The square root of r squared is just r, and then we have the square root of 2 here in the denominator. We can ignore the negative. Obviously, we would have positive or negative r over the square root of 2 in this case because we took a square root. But if we had the negative term, we'd have a negative radius, and we can't have a negative radius because we're dealing with an actual figure in 3D space, and a negative radius would mean that the semicircle and the rectangle didn't exist. So we can just deal with the positive term. So we know now that x is equal to r divided by the square root of 2. Remember, though, that what we really care about is what we've been asked to find in the problem. Find the area of the largest rectangle. So in order to find the area of the rectangle, not only do we need the x dimension, we also need the y dimension, and then we need to plug those into our area equation to find the area. So in order to find the y dimension, we'll plug our x coordinate back into our equation for y, and we'll get the square root of r squared minus r over the square root of 2 squared. And we'll simplify this to get the square root of r squared minus r squared over 2. To find a common denominator, we'll multiply the first term by 2 over 2, and we'll get 2r squared over 2. When we combine fractions, we'll get 2r squared minus r squared just gives us r squared, divided by 2 in the denominator. When we take the square root here, we'll get r in the numerator and the square root of 2 in the denominator. Notice that it's the same value that we got for the x coordinate, so the y and x coordinates are actually equal to one another. And again, we can ignore the negative term. We get obviously positive or negative r over the square root of 2, but we can ignore the negative term because y has to be a positive value. And our last step, of course, is just to find the area because that's what we've actually been asked for. So we'll get the area is 2 times the x coordinate, which we know to be, or the x value, which is r over the square root of 2, times the y value, which is also r over the square root of 2. And when we simplify, we get 2r squared over 2. Our 2's will cancel, and we'll see that the area is equal to r squared. This tells us that the area of the largest rectangle that can be inscribed in a semicircle that has radius r is r squared. Now, since we have this equation, we can plug in any value for the radius r and automatically get the area of the largest rectangle. So if we're ever told that the radius is 4, we know immediately that the area of the largest rectangle will be 16. If we're told that the radius is 10, we automatically know that the area of the largest rectangle will be 100. So we can use this equation with any value of r that we're given. So I hope you found that video helpful. If you did, like this video down below and subscribe to be notified of future videos.